So these are some targeted questions. What I thought I'd go through is file size with a lot of you, because I don't think you fully understand how it works in terms of megabytes, bits, bytes, all of that. So it's good to go back over that. But there are also, as you can see, there are some questions in there about the CPU as well. File size questions come up every year, and you've got to make sure you can understand the maths involved. Now, before I go over this question, all right, the key bit of information here is that there is a 10 by 8 grid, okay? So that means that each pixel has a number of bits allocated to it, all right? So it asks you to work out the minimum file size that would be required to store a bitmap image. That's your key word there, the minimum file size, all right? Now, I want you to have a look at the colors available that you can see, all right? How many colors can you see from that image? Three. Okay. So that kind of gives you an indication of how many bits. Now, where people would go wrong is straight away they would write down that there's a multiplication of 3 somewhere. No. All right? I want you to think about this logistically. Yes, there are 3 colors available, but how many bits represent 3 colors? I need 2 bits to represent 3 colors. I know I could represent 4 as well, but a minimum of 3 bits would be required. Do you want to know why? If I just write this out for you, 0, 0 would be, say, white, 1, 1 could be black, and 0, 1 could be grey. And if I really wanted to, I could have another shade of grey if I wanted to, alright? But realistically speaking, remember, you can only represent 2 colours with a 1 and a 0, on and off, alright? So you need to take that into consideration when you answer this question. There are always questions like this in the exam, and you've got to be prepared for them. So let's first of all look at how we work this out. There is an 8 by 10, alright, a 10 by 8 grid, alright? So 10 times 8 will give you 80, alright? So I now know, alright, I've got 80 pixels to work with, yeah? Well, each pixel is going to have how many bits? 2, because we've worked that out. So 80 times 2 is? Right. That is 160 bits. Yeah? Because we've worked out that we need 2 bits per pixel. But the problem is, it wants it in bytes. How many bits go into a byte? 8. So what am I going to have to do? Yes. Divided by 8 to get into bytes. So that would give you a grand total of 20 bytes you should have got for that. Alright? So work through the process of thinking how many pixels. Alright, so once I've got how many pixels, how many bits are allocated to each pixel. So, for example, if I wanted to represent 16, this is where people get confused often, alright? If I wanted to represent 16 colours, 1, 2, 4, 8, what does that add up to? It adds up to 15. But why is it 16 colours? Because you can also get it turned off as well, which counts as a condition, an outcome. So therefore it's 16. Alright? So hopefully that helps you understand that, because that's often where people go wrong. Alright? So the next one we have, so we're going to move on to the next question. Describe why sound must be converted into a digital format before it can be stored onto a computer. Well, first of all, you need to acknowledge, so this one's about sound compression, you need to acknowledge that sound is analog. Yeah, sound is in its purest form, alright, before it gets onto the computer. So we need to convert it into a digital format. So it says why sound must be converted. Well, originally is analog. Sound isn't recorded digitally. It's recorded every single piece of information. What were you going to ask?
How did you say like it's a wave and it starts off?
So you can say 3 possible ways. You could say sound is either analog, continuous, or a wave. That all is one mark, whichever way you've said it. The other way to get your second mark, all right, is that you need to acknowledge that computers are not analog. Computers are not analog and only use ones and zeros. Okay? You could even say use binary, or you could even say binary there. So you need to acknowledge that the computer needs to have an analog to digital converter, basically. Yeah. So maybe in another question, but not in this one. So I am going to move on now. All right. Hopefully this was really helpful, because there's another question that's very similar coming up. All right. So what we have here again is a question that's got lots of information that goes with it. All right. A sound engineer is using 2000 hertz. All right. What that means is 2000 samples a second. All right. If you ever see HZ, it means that's the number of samples per second. All right. And a sample resolution of 4 bits. All right. What is the maximum file size for a 5-second recording? So we know that's how many samples a second. That is how many bits. And we know there are 5 seconds. So let's work it out slowly. All right. The first thing that you are going to need to do, all right, is work out if I've got 2000, all right, samples a second, all right, I'm going to need to multiply that, because every sample has how many bits in it? 4. So I'm going to need to multiply that by 4, which gets me basically 8,000 bits per second. Does that make sense how I've got that? Yeah, so I'm literally using 8,000 bits every time I'm sampling, every second of music, all right? Now, how many seconds have I got? 5, okay? So that's per second, times 5 seconds. There are 5 seconds available. What is that going to give us?
40,000.
Good, so that is 40,000 bits in total. Right, let's have a look here. It wants our answer in bytes. What am I going to have to do to 40,000? Yes, because this is in bits, and there are 8 bits in a byte, divided by 8. So that should give you your answer of 5,000 bytes. Hopefully the logistics there. There's another one coming up which will explain kilobytes, so you should be able to work this out. Any questions so far on how I got there? So there were 20,000, there were 2,000 samples a second. Each sample is worth 4 bits, which is why I worked that out, which is 8,000 bits per second. Times it by 5 seconds, which gives me 40,000. I've divided that by 8 to get it into bytes. All right. If I had to get, so I've got it in bytes. If I had to get it into kilobytes, what would I have to do next? Divide it by 1,000. Yes. We know that computers times by 2 each time. All right. So really, it's 1,024. But for the purpose of your exam, they accept 1,000, which is why you're not allowed a calculator. Okay. So don't worry about whenever you've got to go from bytes to, megabytes and kilobytes and all of that. You can divide it by 1,000 to do it, okay? All right. Let's look at this one. A sound engineer currently uses a sample resolution of 4 bits, which enables the sample to be stored in 16 different bit patterns. So it's even giving you an answer here to help you. She wants to increase to the number of bit patterns available from 16 to 32. Shade one lozenge which shows the minimum sample resolution in bits. Now let's do this in the process of elimination here, really. If I use 3 bits, 1, 2, 4, which is 7, 4, 5, 6, 7, plus the 0. How many colours can I represent? 8 possible outcomes there, alright? If I use 5,
You can do 32, right?
2, 4, 8, 16, yeah? If I turn all of those on, what does it represent? 16 plus 8, well we know that that's 15. What's 15 plus 16? 31. But then you've got the 0, which is another outcome, so that is 32. Alright? So you always count. It's like when we index when we're programming and we count the 0 as our first. Yeah, we do the same when we're working out the number of bits. Alright? So your answer to that should have been 5. Now, they always try and catch you out on these word problems when it comes to sound sampling. Alright? It's quite a clever way of doing it because you might look at the first part and if you haven't read the second part, it's going to catch you out. So it says, shade one lozenge to show the following states of the effect on the sample rate. So, on increasing the sample rate. Well, I want you to think about it this way before we even answer this question. Look, if I've got this sound, alright, if I've got 4 samples, alright, look at how much of the sound is missed in the middle, yeah? So, and imagine I've got 4 bits per sample. If I add another 4 samples to that and increase the sample rate, alright, so I've added another 4 bits, that was 4, 8, 16, add another 16 to that, that's 32 bits were needed there, so that shows that 32 bits were needed. It increases the file size, but look, the more samples I get, the more parts of the sound I'm getting, which means the quality is going to be better, isn't it? Yeah. So if you can visualize it, some of you are visual learners, so you might prefer seeing this drawing of a sound wave here, but look, if I'm not going to decrease the quality, am I? Because I'm getting more samples, I'm getting closer to the original sound. So, okay, we know it's not that, alright? Has no effect on the quality of the recording or file size. Well, we've just worked out here that if each sample is worth so many bits, so if I add more samples to it, the file size is going up, so it's not that. Improves the quality. Well, we know that it improves the quality because I'm closer to the original sound, but this says has no effect on the file size. Therefore, that is wrong. Improves the quality of the recording? Yes, it does, because I'm closer to the original sound. The more samples, the closer I get to the original sound. Can you see what I'm getting at there? And the file size increased. So therefore, we should have put D as our answer for that. Right, we got another file size one here coming for you. But you'll be pros at it by the time we're finished. So, what's the minimum file size for an 800 pixel by 1000 pixel image that uses 20 different colors? We're going to take this bit by bit first, okay? So, the first thing we know is that we have 800 by 1000. So let's do that. 800 times by 1000, which gives you 800,000. Good. I can say confidently I've got 1 out of the 3 mark scheme there, alright? Even just by working out the grid size, you always get a mark. So if you mess up the rest of it, just make sure you get the size of the grid, okay? Right. 20 different colors. This is where you've got to think about how many bits I'm going to need. I know that 1, 2, 4, 8 makes 15, plus the 0, which would be 16 possible colours. That means I've got to go up 1 bit to be able to represent 20 colours. Alright? So how many bits am I going to need? 5, not 16. 5 bits. Okay? So I know there are 5 bits. That now means that what I've got to do is multiply this by 5, which gives you 4 million. Okay, and that would have been another mark for acknowledging that. Now, look at what it says here. It says it wants your answer in kilobytes. We've got it in bits. So I've got to get it to, if this is 4 million bits, how do I get that into bytes first? Let's think about it logistically. What have I got to do? I've got to divide it by 8, which now gives me, well done, 500,000, but that's only in bytes. Okay, how many kilobytes are in a byte? 1,000. So what have I got to do to this? Divide it by 1,000, which now gives you your final answer of 500 kilobytes. Alright? So, let me just recap on that. So I've worked out the size of the image. Alright, so the grid of image. You don't necessarily need to write this. This is me helping you understand. Alright? Then, I worked out how many bits I needed to represent 20 different colours. So I showed that was, if 4 bits is 16, so I know I need to go up at least 1, alright, which was 5 bits. So that was 5 bits times 800,000, because I've worked out the grid size. Alright. Then, that gave me 4 million bits. I've divided it by 8, because I wanted to work out bytes first. Alright. Which then gives me 500,000. To get it into kilobytes, because 1,000, it's actually 1,024, but for your exams you're allowed to round it to 1,000, okay? But 1,000 bytes is a kilobyte, so that was why I divided it by 1,000 to get to 500, okay? Now, let's go for something a bit more simpler. Convert the binary number into decimal, alright? All you needed to do, for those of you, again, that are more visual, I'm going to write the number out. Now, if you get a 2 marker, you need to show you're working out. This is only 1 mark. You don't need to do this, okay? I'm just doing it so that you can see how I got to my answer, okay? So it was 128 plus 64 plus 16 plus 4, which should give you 212. Alright? Now, we have a binary shift question. We know that if we go to the left, what happens to the number? Yeah, it multiplies by 2. Avoid using the word double. Show that you understand the multiplication. If we go this way, we divide by 2. So then, look what's happening here. It says a shift of 2 is to that it will be multiplied by 4. Alright? Now it says state the arithmetic. So we've actually given you a little bit of help here. State the arithmetic of applying a left binary shift of 3 followed by a right binary shift of 5. Okay, so look, if I had to I'm going to basically go multiply times 2 times 2 times 2, which is multiplied by 8. Yeah, so that would be multiplied by 8, but then it says followed by a right shift of 5. So if I go back, that's going to be times, that's going to be divided by 2, divided by 2, divided by 2, alright, which basically gets you back to 0, alright, where you started. I'm not saying the answer's 0, alright, it's just about where you started, but then you've got to do a right shift of 5. So we've done 3 shifts, 2 more would be divided by 2, which would be divided by 4. Yes, well done. When it comes to binary shifts, as long as you can work out, I went that way, that way, that way. Then I went that way, that way, that way. So you can see that that was cancelled out. So I then know I'm back to where I started, divided by 2, divided by 2. Yeah? Now, let's go through some more of these to help you. Okay, the best way to help you with, do you know what, binary addition, some people just open up the paper and look at it and scream and go, oh my gosh, what's going on, alright? But if you know what 1, 2, and 3 is in binary, this is easy. Look, the number 1 in binary is 1. The number 2 in binary is 1, 0. The number 3 in binary is 1, 1. Okay? If you know that, it's just the same as carrying when you add decimal numbers together. Because watch. 0 plus 0 plus 0 is 1. What's 1 in binary? 1. What's 1 plus 1? 2. What's 2 in binary?
1, 0.
1, 0. But we have to carry a bit. 1, 0. What's 1 plus 1? 2. Carry the 0. Sorry, carry the 1. 0 plus 0 plus 0 plus 1 is 1. Good. 1 plus 1 is? It's 2, so 0, carry the 1. Now this time we've got 3. Look what the rule is. 3 in binary is 1, 1. So 1, carry the 1. And then again 0, 0, 0, 1, 0, 1, 0, 1. So that's what your answer should have been. And generally speaking, when you do these in an exam, alright, this one here is your first mark and this one here is your second mark. Alright, so even if you mess up part way through, usually you'll get 1 mark for getting one part of it right. Okay? Now this one. I'm more visual when it comes to this. A lot of people would work out the number. Some people like the division method where you actually work out what it is in decimal and divide it by 60. Some people like that. I personally prefer to do it this way. Alright? So I tend to write out what the number is. And I've split it into 2 nibbles. Yeah, remember 4 bits represent 1 hex, okay? So I know that that is 1, 2, 4, 8. 1, 2, 4, 8. What number is this?
9.
Number 9. What is this? 8 plus 2 plus
11.
So that's 11, okay. But remember, with hexadecimal, it goes 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A. B, C, D, E, F. So you should have had B, 9, as your final answer. Alright? Okay. So let's have a look at question 8. I'm only going to give you some bullet points here to help you with this. Alright, I'm only going to give you some bullet points here, but it's worth 6 marks and it's generally about the quality and your understanding. There are several CPU characteristics that can affect its performance. One of these is clock speed. Can guarantee that people will talk about clock speed on how to improve it and they've ignored the point that they said you're not allowed to talk about. Explain how one other characteristic can affect the CPU performance. So you can guarantee, just by misreading the question on your exam technique and starting to write about your clock speed again, you're going to basically stop your marks, okay? So, in this question, you'll be marked on your English and to organize information. Yes.
Isn't it supposed to be about both of them? So?
Yeah, it does say.
Yeah, how clock speed and, sorry, yeah. One of these is called explain, but what I'm saying is some people will only go and talk about clock speed, but not talk about how they link together. All right. So, all right. So, what we could have talked about there is you could have talked about the cache. You could have talked about so other characteristics. So let's look at the cache first. So you explain how the clock speed and one other. So let's look at clock speed first. All right. First of all, can you acknowledge that clock speed is the number of fetch, decode, execute cycles per second, okay? These are carried out on a clock pulse. So what you've got to acknowledge there is the faster the clock speed, the more processes. So I'm obviously writing this in bullet point format. You need to obviously articulate this in like paragraphs, okay? But the faster the clock means more pulses and more instructions or fetch, decode, execute cycles processed. Alright, whereas the other thing that you could do to improve the performance of the CPU is you could actually talk about the number of cores. Alright, you can say whereas the clock speed improves performance, cores, alright, all have their own clock speed. Alright, by having more cores, you can, so this is where you got to acknowledge, you can process instructions parallel / at the same time. Alright, this means that you can process twice as many instructions, and I want to say, in case you get a really long question, so I'm just going to put times 2 instructions if the application uses multiple cores. You might want to even acknowledge that in some applications that cores are given different jobs. Like for example, I could have one core that is working on the graphics and one core that's working on the mathematical elements. The other thing that people might have talked about is they may have talked about the cache. Alright? The cache holds the frequently used instructions / data. Okay, I'm going to show you here. Now, if you've got a bigger cache does cost money, by the way. If you've got a bigger cache, all right, then it means you've not got to go to the RAM as much to get instructions and data because it's already loaded into the cache, which speeds up the processing. So if your instructions and data are not in the RAM because they're in the cache, the CPU is getting the instruction a lot quicker. This is what this is talking about here, all right? And it's closer to the processor, so you're not having to go all the way up the buses to go and get the data, okay? Now, we are going to, I am aware of time, so to finish off this session, the last question says, memory and processor are two essential pieces of hardware. Explain with reference to the memory and the processor how the computer processes instructions. Well, let's have a look at this. Alright, here are your points. You need to know how the CPU works. So, we know that the instructions, I'm going to say the instructions and the data are held in memory, okay? In case you get an even longer one, this is only 4 marks, but the instructions and the data are held in the main memory, in the RAM. These instructions, alright, are usually loaded from the secondary storage device into the memory. So if you've got a hard drive, alright, think about it, when you load up an application that is taken from the hard drive and loaded into the RAM. So the fact that when you open up Microsoft Word, when you open up a game, when you start up your computer, the operating system is loaded into the RAM so that you can run it, okay? So that's moved into the memory. Instructions are stored in a contiguous format. The processor fetches the instruction from the main memory, decodes that instruction, and then executes it. Now, if you want to remember the registers, which are important to you, the result is stored in the back into the memory, but if you want to talk about the CPU, it's held in the accumulator before, right? The result of when you decode something, the result of that is stored in the accumulator before it's moved back to the main memory, okay?